All right, so this section is on logarithms, logarithm functions, and getting these ideas out. So, logarithm, basic definition. So these are related to exponential functions. In fact, a logarithm is the inverse of an exponential function. We'll talk about that when we get to the graph. So for some constant a greater than 0, a not equal to 1, and x greater than 0, here is the definition of a log. So y equals log base a of x means that a to the y equals x. And so this relationship is very important when it comes to converting between exponentials and logarithms. Sometimes when we have an exponential equation, we can't solve it without converting it to a log equation, and vice versa. So it's important to remember this. It's important to understand it. And so we have some examples here, equivalent expressions. So log base 3 of 9 equals 2. So now what does that mean? So when you see, if you didn't have the 2, so it's just what is log base 3 of 9? What does that equal? It's essentially asking what 3 to the what equals 9. So what exponent do we need? And of course that's 2. So 3 squared equals 9. And so the way you can kind of remember this, at least the way I remember it, this is called the base of the logarithm. So the subscript 3 here is the base of the logarithm, where a is the base. Now, you may not hear this a lot, but the base of the 3 is the base of this exponent. So 2, of course, we know is the exponent. 3 is the base of the exponent. And so the base of the log is the same as the base of the exponent. And then as far as just kind of a way to remember this, 2 and 9 switch sides of the equal sign. So here with the log, 9 is on the same side as the 3. Over here in the exponential, 9 is on the opposite side, and vice versa for the 2. So that's kind of how I remember how to convert these. Generally speaking, it's probably a good idea to have one like this that's easy to remember. So formulas with just variables in them may or may not be easy to remember. But I think if you remember, we all know 3 squared equals 9. And if you remember log base 3 of 9 equals 2, that's a good one to remember. And then you can convert this to other expressions and equations. All right, so log base 10. Now, most of the time we don't write the base 10. Most of the time we would just write this as log of 100,000. So if you put in your calculator log some number, the base is assumed to be 10. So most of the time we don't write the 10, but we could write this equivalently as 10 to the 5th equals 100,000. Then similarly here, we could write this as 4 to the negative 3 equals 1 over 64. And then last, E, we talked about E at the end of the last video. So E is just the irrational number approximately equal to 2.71828, on and on, it's like pi. And so there's just e to the 0 equals 1, which of course any number to the 0 power is 1. All right, so you'll have some on the homework where you have to go from one side to the other. You will have some exponential forms that you have to convert to logs to exponentials, both ways. All right, one thing you might, I guess it depends on your college algebra pre-calculus course, how much you get into these. The graphs of a log function. So again, a is greater than 0, a is not equal to 1. Now one thing, notice that this is the same as the parameters around the exponential function. So when we had an exponential function y equals a to the x, this is exactly what we said about a. And the reason is because, again, a log function is the inverse of an exponential. So a can only be the same things. It can't be one thing in an exponential and a different thing in a log. So if it can't be negative here, it cannot be negative here. So if a is greater than 0 and a is not equal to 1, then the logarithmic function of base a is defined f of x equals log base a. All right, now notice on the graph. So let's compare these. So we have an exponential function, we have a log function. So here we have f of x equals 2 to the x. Here we have g of x is log base 2 of x. So these are inverses of each other. And you notice we have the ordered pair 0, 1. We have the ordered pair 1, 0. We have the ordered pair 2, 4, 4, 2, and so on. So when we look at inverses, we can notice some things like the domain and like the range. So if we look at the domain of the exponential, the domain is all real numbers. And then the range of the exponential is 0 to infinity. Now, when we have inverse functions, the domain and range switch. So any two functions that are inverses, all the ordered pairs are switched. So that means that the domain and the range are switched. So the domain of a log function is 0 to infinity, and the range is negative infinity to negative infinity to positive infinity. What about asymptotes? So this is kind of the other important part. The asymptote of an exponential function, just the basic one, of course, if you start shifting it, it moves, but just the basic one is y equals 0. So this one goes out and gets closer and closer to the x-axis. And so if you have a horizontal asymptote, so that's a horizontal asymptote, when you do the inverse, that will be a vertical asymptote. And it's not y equals 0, but it will be x equals 0. So these are inverses. It's important to keep that in mind as we go along. Now, next thing we probably have seen in other classes, but it's good to remember. This will be helpful, so we will see this again later. And we will be using logs as we go along through this course. So the first property, log of xy, we can expand that. I'm not going to write the base a, but the base a will apply, is log of x plus log of y. Log of x divided by y is log of x minus log of y. Log of x to the r, so the r we can bring in front of the log. So this becomes r times the log of x. And then log base a of a. So this, so you can think of this as a to the what exponent equals a, and of course that is 1. So this is going back to the equivalent expressions. If we convert this to an exponential, we would write a to the first power equals a, which of course makes sense. Similarly, log base a of 1 is 0 because anything to the 0 power is going to be 1. And then log base a of a to the r is just going to be r. And again, we could write a to the r equals a to the r. So these you certainly need to know as we go along. They will come up from time to time, be very useful. All right, so rewrite the following logarithms. So we're just going to combine these into one. So we have log of x plus log of x minus 1. So we have plus here. So that means we're going to multiply these two. So log of x times x minus 1. And that's probably good enough, but if you want, you can distribute that x and get x squared minus x. Then the next one, we have log of x squared minus 4x over x plus 6. So the division, we're going to be subtracting that. So log of x squared minus 4x minus log of x plus 6. And then last one, log of 9x to the 5th. So we have 9 times x to the 5th. So the 5th, it's important to remember, the 5th only applies to the x. It does not apply to the 9. If the 5th was out here, outside the parentheses, then you could go ahead and put it in front of the log. But you can't if it only applies to one thing. So first we need to split this. So let's write this as log of 9 plus log of x to the 5th. Now we have x to the 5th, so we can bring that 5 in front of this one. So log of 9 plus 5 log of x. All right. So this next thing, change of base theorem. This is really mostly applicable for entering different base logarithms into the calculator. So most calculators, there are a few versions of the TI-84, maybe TI-83, but I think mostly the TI-84, which we're not using any of those. So I'm not sure that any calculators we'll be using in this course can do other bases. But you have the log button on your calculator, and the log button on your calculator only does base 10. So really, when you do a log on the calculator, you put log of 23, it's log base 10. And there's no way to do another base just strictly like that. So the way to do it is to use this formula. So log base a of x is the same as ln of x over ln of a. So here you have your base. Whatever your base is goes in the denominator. And then this is just whatever you're taking the log of originally. All right, so keep that in mind. I think there are a couple on the homework where you're just putting it in the calculator, and that's how you'll do that. All right, so solve this equation. So the first thing you need to do with a log equation is combine the logarithms. So we'll use the properties that we learned. So log base 2, and I will write the base. You always need to write the base, but sometimes if it's not that important, I won't do it. So combine these with multiplication, that equals 3. Now, once you have a one log expression equal to something else, a non-log expression in this case, now let's convert this to an exponential equation. So base 2 to the third equals x times x plus 2. All right, so 2 to the third is 8. Let's multiply it, distribute the x, and then we can subtract the 8. And then we can probably factor this, then we get x plus 4, x minus 2, and x is going to be equal to negative 4, x is equal to 2. Now this is the answer. This one is not the answer. Now, why? Because you cannot take log of a negative. If you go back to that graph, we said the domain of log of x is 0 to infinity. So there are no negatives here. So you cannot do log of a negative number. So when you plug in negative 4, of course you have log of negative 4, which you can't do that. And then even when you plug in this one, log of negative 2. So it's not necessarily that this is negative. The important part is when you plug this in, you're plugging in a negative number. So for instance, if we just had log of x plus 2 equals whatever, and let's say we get x equals negative 1, that is perfectly fine, because then we're just doing log of 1, which is okay. So it's not that you get a negative, it's that when you plug that in for x, you're taking log of a negative after that. All right. Next one. So this one's a little bit trickier. You'll definitely need a calculator for this. And so in the previous section, when we saw an exponential equation, we would try to get the bases to be the same. And the example I think that we used was 25 was one base, 125 was the other. And so we could write both of those as 5 squared and then 5 to the third. And then it's pretty easy after that. But there's no number that you could write where it has the common base and gives us 2. So the easiest way to do this is to just take the ln of both sides. Or you could do the log, either way. Ln of 2 to the x plus 1 equals ln of 3 to the x. Now we're going to use our properties of logarithms and bring this exponent down, bring both the exponents down. X plus 1 ln of 2 equals x ln of 3. And I don't remember if they want this unsimplified or not. So we will leave it unsimplified for now. So let's distribute. So ln of 2 is just a number. Ln of 3 is just a number. So let's write this. We'll distribute this ln of 2. And you want to be comfortable. I mean, this may make you uncomfortable to have to do this with the LNs in it, but you really probably should be comfortable doing it at this point. And if you want, you can put in the number, and then, although if it asks for an unsimplified answer, then, or an exact answer versus approximate, then you probably need to leave it this way. So we have xln2 and xln3. Let's subtract those and get those on the same side. Now, what we can do is we can factor this out. So ln of 2 equals x ln of 3 minus ln of 2. Now use the properties logarithms. That gives us ln of 3 halves, 3 divided by 2. So ln of 2 equals x times ln of 3 halves. Now divide both sides by ln of 3 halves. So x equals ln of 2 over ln of 3 halves. And then if it asks for an approximate answer, you can put that in the calculator, but that may be what it wants. I don't remember what my math lab wants, but I do think that you should be able to do it this way without using the calculator. And if you need an approximate answer, you can get an approximate answer. But if it doesn't say round to 4 digits or whatever number of digits, then this is the answer that it wants. So a lot of times people will solve a problem and it wants the exact answer. So it wants something like this, or even something like 1 plus square root 2 maybe is the answer to a particular problem. And this is an irrational number. It doesn't say to round, so that's what it wants. But then some students don't realize that, and they put that in the calculator and round it off at 2.414 or whatever. And then it counts that off. So if it doesn't say to round, you need the exact answer, which would be this. If it does say to round, then you put this in the calculator and round to wherever you need to round to. All right. Next change of base theorem is an exponential. So a to the x is e to the ln of a times x. And the reason this works is e to the ln of a equals a. Just like we could also say that ln of e to the a equals a. So there's just an easy way to sometimes, or a way to make problems easier sometimes. May or may not use it throughout the course, but we probably will at some point. All right, so this is similar to the one we did earlier. So we need to convert this to an exponential equation. Anytime you have a log of something equals a number, convert it to an exponential. So we have 6 to the third equals 2x minus 1. 6 to the third, I believe, is 216. Yeah. So 216 equals 2x minus 1. So we get 217 equals 2x. And so x is 217 over 2. And of course, when we plug in 217 over 2, that of course will give us a positive number. And so it works out. All right. Next one, we have log base 2 t plus 32 minus log base 2 t plus 5 equals log base 2 of t. Okay, so now this one, what we cannot do is cancel out these logs. So if you have multiple log expressions on one side, you cannot cancel them out. You got to combine these first. So we have the subtraction. So let's combine these with division. So t plus 32 over t plus 5. And that equals log base 2 of t. So now log base 2 and log base 2, now we can really just get rid of these and just have t plus 32 over t plus 5 equals t. Now let's cross multiply. So we have t plus 32 equals t squared plus 5t. subtract, let's set this equal to 0. So you have t squared plus 4t minus 32. And I think this will factor into t plus 8 and t minus 4. And so we get t equals negative 8, and then t equals 4. And of course, this one will work, and this one will not. And the reason this will not is because when you plug it into this one, you get log of negative 3, which doesn't work. If it would work in this one, it would also not work in that one. So if this is our only log, negative 8 might be fine, because then if you plug in negative 8, you get log of 24, which is okay. So most of the time you're going to throw out the negative answers, but it's not guaranteed. It is possible to have a negative answer to a log problem. Okay, and then the last one, we have log base b of 2 equals a. Log base b of 3 equals c. And now we need to figure out what log base b of 144b is. All right, so what can we do here? So first of all, we have 144 times b. So let's separate these with our property where we can use addition. This one is going to be 1, if you remember from one of the properties says that. Now, let's write 144 in terms of 2 and 3. So 144 is 12 times 12. I'm going to write a plus 1 for this one. Log b, we can separate these. 12 plus log b, 12 plus 1. All right, now 12 is 2 times 2 times 3, or we could write 2 squared. Log 2 squared times 3 plus log 2 squared times 3. There's probably an easier way to do that. Now I'm looking at this, we could have written 12 squared here and just brought the 2 in front, but we'll keep going the way we're going. All right. And in fact, we'll just combine these two. So we have 2 of these guys. So let's just write equals 2 log base b 2 squared times 3 plus 1. So now let's separate these two. So log base b 2 squared plus log base b of 3 plus 1. And then we'll bring this exponent in front. 2 log base b of 2 plus log base b of 3. And so now we can plug these two things in. So log base b of 2 is a, log base b of 3 is c. So this is 2 times 2a plus c plus 1. And then we'll distribute that 2, and we get 4a plus 2c plus 1. And there you go. Okay, so most of these with any kind of log problem, most of the time you're going to use one of the properties, and usually whatever you can do is something that you should do. And so there's not going, if it's a legal step, it's probably not the wrong step. So know these properties well enough that you can pull them out whenever you might need them, and confidently be able to do them, because if you do one wrong, then of course you get the wrong answer. But if you can do something, probably it's the right step. So just keep that in mind as we go along. All right, we'll see you on the next one.